For our senior design capstone project for mechanical engineering at the University of Utah, L3 Harris requested our team design a device capable of tracking aircraft based off of ADS-B data. Starting January 2020, aircraft are now required by the FAA to transmit ADS-B, or Automatic Dependent Surveillance Broadcast data, which transmits the aircraft's position, altitude, velocity, and identification information. L3 Harris would like to determine how accurately an in-flight aircraft can be visually tracked using this data.
Our system requirements mandate that our device must visually track in-flight aircraft with an accuracy of 0.1 degrees of rotation. It also must weigh less than 20 kilograms or 40 pounds while being able to withstand harsh environmental conditions. Finally, it must wirelessly relay video to the user via remote operation. This shows our overall construction of our device. From the left, we have a close-up of our digital imaging scope and voltage regulator, which is used to smooth out the incoming voltage from the power source, followed by a couple of shots detailing the orientation of the Goal Zero portable power station, the servo motors with their corresponding gear trains, and encoder positioning and wiring solutions. Lastly, on the right, our electronics case showcases our thermal regulation and venting design.
In order to use in outdoor conditions and maintain uninhibited rotation, the weatherproof electronics case was affixed to the pedestal arm. This case contains all control components. The components in the box are a Latte Panda with a Windows 10 Pro operating system, an Arduino Mega integrated into the Latte Panda, a 5-volt bus in the upper right corner, and for ease of access, a servo proto board and an encoder proto board. Also, there is a temperature-controlled fan circuit for the bottom ventilation fan. The box was also equipped with louvers on each side for ventilation. Here is a demonstration video of the convective airflow to alleviate the heat buildup in the enclosure. As you can see, the smoke demonstrates good air movement between the fan at the bottom to the louver vents out of the sides.
The system is controlled using a remote-in connection and a Python-based graphical user interface, or GUI. The ADS-B receiver collects the data from the ADS-B transmitters on the aircraft and populates a selectable list in the GUI with aircraft tail numbers. The user can then select the tail number of the aircraft they'd like to track, and the system will start tracking that aircraft. A PID controller is used to refine the system movement and increase device accuracy. Here's a close-up of the user interface. The selectable tail number list is on the left, where a user can select the tail number of the aircraft they would like to track, and the system will begin tracking that aircraft. The bottom right displays a live string from the scope, allowing the user to see what the device is seeing in real time. The GUI also records and saves the video feed from the scope as it is running. The upper right field is a placeholder for a map of the geographic area surrounding the device for displaying aircraft locations that can be implemented by future developers. This clip shows the device panning to a home position. It will then point to a theoretical aircraft location for demonstration purposes. The device is capable of 360 degrees of panning rotation and 90 degrees of tilt rotation.
Throughout the semester, we've worked on developing the device with these 7 milestones in mind. For ease of understanding, they're color-coded. Green means good, yellow means in progress, and the orange means still untested. So for final results, our motor position was well within the metric of success at 0.036 degrees precision between the optical encoders we used and the PID controller we used to control the motors. Our thermal solution was effective as the electronic case is sufficiently ventilated in order to cool the Latte Panda, as demonstrated by the smoke test. Remote operation of the device is possible through Windows remote desktop connection, and there is very little lag between data transfer from the Latte Panda to the Arduino board running the device. The device is lightweight and compact, weighing in at 17.5 kilograms, which is well under the 20 kilograms we were given. And this does include the carry case and tripod. The device rotational speed is well above the metric of success we had set for ourselves at 4.75 rotations per minute. Our device tracking and accuracy should theoretically be able to work. We should theoretically be able to track planes. However, we were unable to test this due to integration issues. Finally, for bore sighting, this remained untested due to the time constraints we faced. So in conclusion, we believe that our device is a good base point and proof of concept for tracking planes based off of ADS-B. There were numerous things we accomplished through this. We were able to receive and interpret ADS-B data. We were able to integrate a Latte Panda and an Arduino board in order to send data from Python to Arduino. We were able to develop a robust control system for these motors in order to get accurate movements. And then we were also able to develop a thermal solution in order to operate this Latte Panda board in outdoor conditions. Unfortunately, we were unable to track airplanes in this project due to the numerous hurdles that integration threw at us. Ultimately, we tried to bring together numerous components that were already designed, which resulted in issues with integration and compatibility. However, we do believe that this device is a very good base point for L3 Harris to develop into an actual product for their use.